David Hilbert was born in Königsberg, Russia, on January 23, 1862. David went to school in Königsberg for his formal education, and he also attended the University of Königsberg, where he gained his doctorate in mathematics and would stay to teach for 11 years. After getting married in 1892, Hilbert began teaching at the University of Göttingen. At this university, Hilbert would teach and research for the rest of his life. Hilbert worked on many mathematical theorems and helped to define modern geometric axioms still used today. One of Hilbert's most interesting theorems was that of a grand hotel of infinite size and rooming capacity, with problems arising as to the possibility of fitting more guests into a full hotel. This is the theorem we will be focusing on. Imagine, if you will, a hotel made of an infinite number of rooms accommodated by an infinite number of guests.
Suppose a new guest comes into a hotel and asks if he could use a room for the night. The clerk tells the guest that all the rooms are full and asks him to leave. The guest says, well, that shouldn't be a problem. Just ask the guest in room 1 to move to room 2, the guest in room 2 to move to room 3, and so on. This way, there will no longer be any guests occupying room 1, and I can stay the night. The clerk, most excited, does just as the guest asks, allowing a new guest to fit into the hotel that is infinitely full.
This situation describes a way in which any finite number can be added to infinity to yield a result of infinity. The process of moving a guest down one room works because even though all the rooms are occupied, there will always be one more room the last guest can move into. In this way, even though one guest is always being displaced as long as the extra guest remains in the hotel, it is of no consequence to the rest of the guests in the hotel, since they will all be given a room event.
The fact that you can fit more people into a full hotel is not a contradictory paradox, but a logical paradox. This situation demonstrates the property that any finite number added to infinity still yields the result of infinity. However, there are still more situations the Grand Hotel can help describe.
What if, instead of a finite number of guests, an infinite number of guests request rooms for the night? There is a solution, and it involves moving all the guests into the room that is 2 times the number of the current room they are in. In this way, then all of the odd rooms are free for new guests to occupy because all numbers multiplied by 2 are even. Again, this is a strange situation as there will always be people shuffling rooms, but at one point or another, the majority of the guests in the hotel will be in a room all to themselves. The purpose of this situation is to prove the fact that infinity can be added to infinity to yield an answer of infinity.
There is one final situation which can be described by Hilbert's Hotel. Suppose, if you will, for a minute, a man walks into a hotel and tells the clerk working at the hotel he has an infinite number of buses in his group, each filled with an infinite number of people on board as passengers. All of them need rooms for the night. How would the clerk be able to allow the guests to stay? The answer, my friend, lies in prime numbers. First, the clerk will move everyone to even rooms, as in the situation before. Then, the clerk will assign each bus a different prime number, starting with 3. The first group of passengers would then occupy all of the rooms that are powers of 3. So rooms 3, 9, 27, and so on. Each bus could be allotted one prime number. And because there are infinitely many prime numbers, the passengers of the buses could all be supplied rooms. And because all of the powers of prime numbers are odd, each person can be supplied a room.
Mr. Snap!